All right, everyone. Today I've got another good teaching lesson for you. Today we're going to focus on regression and classification analysis on the same data set. So I've discussed this quite a bit on my channel. What's regression? I've got several videos on that, and what is classification? I've got several videos on that, right? So I'm not going to duplicate or replicate what I've already done. That makes no sense whatsoever. But I want to show you how to do this type of analysis on the same data set. So usually regression is done on a regression type of data set, which is um, numerical data, and classification is done on labeled data. But it doesn't have to be that way. You can certainly do both types of analysis on the same data set, and I'll show you how that's done right now, okay? And there's benefits to doing that too, okay? If we perform this type of analysis on the same data set, we can actually build more comprehensive insights about the data and understand better the nuances of the data and what it's telling us. We can have better customer targeting, or um, whatever type of business we're working on. We can target that type of business, that enterprise, in a better way, right? With more insights, more information, and better understanding of the data. Okay, we can build feature relationships and validation around this data. We can have improved model design and construction of these models and enhanced decision making capabilities, right? So it really behooves us to take a holistic approach to this data and to understand it, so we can build more robust strategies around the execution of whatever type of model we're trying to create and the takeaway from that model, what it's telling us, right? So I couldn't find the exact type of data set that I wanted, so I went ahead and told Python, just create the data for me, okay? I'm looking at age of customers, income, previous purchase patterns, and some type of engagement score. That's what I'm going to create for my data frame. And then I want to understand the overall expected spend from each customer, and then a response to some type of ad or some type of stimulus that we're going to present to these customers. Okay, so we go ahead and hit Control Enter to refresh the view in the cell in my Jupyter notebook, and I'll share all this code with you when I post the video a little bit later today, so you'll have all the code to play around with and to just copy and paste, so you don't have to make notes here, you don't have to type out everything. I'm going to give that to you, run it in your own Jupyter notebook environment, and you should be good to go. And I'm trying to make this generic too, so you can answer your own specific questions, right? If I answer some questions are very, very unique and very specific. That's great for me. It might not necessarily help you though. So I'm trying to make these videos slightly more generic, or try to lean towards something that's more generic, so you can take this and adopt it to suit your needs and to solve your own specific problems. Okay, so we have age, income, previous purchases, number of purchases, right? That's counts, engagement score, and the expected spend from this customer. This is probably on an annual basis. I don't think anybody is spending $10,000 in one shopping spree. And then we'll have a response to an ad. Okay, so we have the fundamental data frame. We're going to go ahead and create our independent variables. This is always the X, and then the dependent is going to be Y regression and Y classification. Okay, so the expected spend is the regression type of problem is numeric, and the response to an ad is going to be a label, 0 or 1. So 0 is no response, and 1 is a response, and that person is going to make a purchase. So we have age, income, previous purchases, engagement score. These are the independent variables, and these are the dependent right here. Okay, so like every other machine learning algorithm, I'm going to do split the data, train the model, and then test it. So here's the split right here. Here's fitting the model. Okay, we've predicted, or we've captured our Y regression predictive variable. Okay, and we're going to measure that against a Y regression test variable to see how accurately this model is learning and how um, proficient it is in making predictions. So we get a R squared of 1%, or 1.0, so that's perfect. The mean square error is 98, and the mean square error is 97.92. So pretty low errors and pretty high um, R squared, right? Coefficient of determination and coefficient of correlation would be the R, right? So that's basic statistics. So let us go ahead now and get the classification done. That was the regression side of the equation, right? Let's do the classification. So Control Enter to refresh the code in the cell, and we will see how well our model was able to well, we did the training, we did the fitting here, and we'll see how competent the model is in making predictions. So we have the Y classify predictive variable right here, just like we had Y regression predicted and Y regression test, okay, and Y classification test. That's how we're measuring our precision, recall, and F1 score. The overall accuracy is 0.86, so pretty decent. These numbers are high. I like to see that closer to 9.5 is better. This is a little bit low in its capabilities, but anything over 0.7 is statistically significant, so that's fine. And we can see the counts in the support column here are equally weighted, so there's no problem with imbalanced data. A lot of times in classification types of problems, you see imbalanced data where you'll see a lot of records in one data set, but not in another. Certainly in credit card fraud, most credit card transactions are not fraudulent. Sometimes you will see fraud, right? But the counts of those fraudulent transactions are much lower, so you can't compare one set, the non-fraud data, to the fraud data, because one is going to be highly imbalanced, with the fraud data being having a very low record count and the non-fraudulent data having very high record count, right? So we want to be careful. We don't have that kind of problem here, so we don't have to handle that. Anyway, we can just run the model as is. If we didn't have that issue, we'd probably have to use SMOTE or some type of technique to oversample from the underrepresented class and undersample from the overrepresented class. That's not a problem, so I think we're good to go here. And that's exactly what I was talking about. Probably could have said it in fewer words. So we have 15,000 records from both classes, 0 and 1. So let's go ahead and make some predictions. So why are we doing all of this machine learning, training, testing, splitting, fitting the model, training the model? What's the point of all this? I've seen a lot of videos on YouTube where they'll stop right here. Okay, they'll make the predictions. Okay, accuracy is 0.86, we're done. And here the coefficient of determination is 1.0, we're done. We're not really done, in my opinion. Like, you have set up the model, trained it, tested it, fit the model, and the accuracy, or the R squared, is very high over here, okay? But we have to take this over the goal line. We're 1 foot away from the goal line. We can't score a touchdown if we're not making predictions. So I've seen these videos on YouTube. I don't know why they don't make predictions. I've seen blogs, data science bloggers, and they'll get up to this point and just stop. But really, the whole point is to make predictions, guys. So when you get to that point, that's good. You're getting close. You're 1 foot away from the goal line, but let's take this thing over the goal line and score a touchdown here. So we have our original data, right? Data is age, income, previous purchases, engagement, and response to ad. And we want to measure expected spend. This is for regression. Remember, this is numeric. Classifiers are label data. So we have, for the classifier, age, income, previous purchases, engagement, and expected spend. And we're looking for the response to the ad, okay? So that's what we're trying to measure here. So let us go ahead and hit Control Enter. Predicted expected spend is 10,061. So if I look over here at age, income, previous purchase, response to ad, I'm going to look for these numbers right here. This is what I'm putting in. So this is a new variable that just came up. And I want to see, based on these values, how well the machine learning algorithm was able to learn and make predictions. So I'm looking at 56, 48,000, 259, and 10,355. So these are the numbers I'm trying to get to right here, okay? And I want to understand, what is the expected spend? I'm sorry, I'm looking for expected spend. This is the regression side. So if the response to ad is 0, engagement 59, previous 2, income 48, and age is 56, I would expect the spend to be around $10,300, okay? Give or take. It's going to be pretty accurate. It's probably not going to be spot on. I'll tell you why in a minute. We run this, we get 10,061. So I was expecting 10,300. It gave me 10,061. Let me see what the difference is. I'm guessing about 2%, 2 to 3%. Let's do the math on this real quick here. It is close. It's not spot on. And the reason is because it's making estimates, okay? So we're not going to get 10,355. I think that's what that was, right? We're not going to get like an exact number here divided by minus 1.02. So it's off by 2%. I probably did that backwards, right? Okay, put that up here, put that up here. Enter. Okay, so it's off by about 2.9%, almost 3%. That's okay. It's making estimates. So if we have this combination of what are we calling this again? Age income, purchase, previous purchases, engagement, and response to ad. We can expect this customer to spend this much. Okay, so we're making a prediction into the future, what's going to happen next. So here's the classifier. Again, 56, 49, 48,000 to 59. Then we have the spend over here. We're looking at the response to the ad. Okay, and the model is saying based on the training, testing, fitting of the model, we can, with these inputs, we can expect what kind of output to the ad. Remember, we're just looking at the first column here. Right here, that's where the numbers are coming from. And we can expect a response of 0. So no activity, no action, no spend from this customer. They're not going to do anything. And that's exactly what we get, 0. Response to ad, 0. So let's look at another example. Hopefully that was enlightening and informative. I think so. Hopefully it was. Let's try to answer the following question. How do we predict revenue, and how can we predict top selling items? So again, this could be anything. Items in a grocery store, a retail outlet, just whatever, fast food joint, could be anything, right? We want to predict revenue and understand the top selling item. So as we saw above, we'll create another hypothetical data set because I don't actually have this data. I looked online for it a little bit. I didn't find anything that was satisfactory to me. So I just created the hypothetical data set to illustrate the point of what we're doing here. Okay, so let me hit Control Enter. Again, I'm going to share all this code with you so you don't have to type it. You don't have to make notes or anything. So let's look at a similar example. Price, marketing, spend, seasonal score, and stock level are going to be the independent variables, and we're going to try to predict revenue. And is this a top seller, yes or no? So this could be a top seller for this item. We don't actually have the item name. We just have an index, but yeah, we should put item names in there, but that's fine. That's fine. If I had to redo this, I would do it slightly different again. But the concept is the same, right? We have the regression and the classification, right? Revenue. This is a continuous data right here, numeric, and this is a top seller. Let's label data 0, 1. 0 is nothing, and 1 is positive, right? So false or false or true, positive or negative, right? So that's what that is. We're doing the splitting down here. So we have the Y classification training, Y classification tests, Y regression training, Y regression tests. Okay, so just like we saw before, go ahead, hit Control Enter. The R squared is a little bit lower. Last time we had perfect 1.0. This is 0.86, so pretty decent R squared. Anything over 0.9 is more desirable. Anything under 0.7, we would really have to reconsider the model. This is, what kind of model here are we using? Linear regression, okay? So linear regression models are great in some scenarios. They're not great in other scenarios. In this case, it's performing just okay. It's not fantastic. We're going to try a different type of regressor here. This is a random forest regressor. Control Enter. Let's see what kind of R squared we get now. We had 0.86 before with the log regressor. Right, log regression, yep. And with the random forest regressor, the R squared is going to be 0.98. Okay, so different model. It's performing better. We got 0.86 over here, 0.98. I think this is a better model. We'll go with the random forest regressor over the linear regressor. Okay, and for the log regressor, now this is always cracks me up. Like, it's called a regressor, but it's actually a classifier. I have to Google this someday because this kind of drives me nuts. Like, this is actually a classification model, but sounds like it's a regression model, but it's actually not. I'm gonna look that up one of these days. Maybe I'll do a video about that. So sounds like a misnomer, but no, it's doing exactly what it's supposed to do. Here's the accuracy 0.97, and the precision, recall, and F1 scores are pretty decent, high 9s across the board. So it looks like recall has improved, right? And this is great. This is great. The model is doing what we wanted to do. We're going to go with the log regression. The performance is good, and the random forest regressor. The performance is good. It's better than the linear regressor. So let's go ahead and re-input these values into the model. We've trained it, tested it. Now we're going to make predictions. So we have 0.82. I probably took this from the first line. Let me see. No, I took it from last. Okay, so 0.82, 953, 0.48, and stock level is 6. And we're trying to predict this number right here, 17,857. Okay, so let's go ahead and run it. and we have 82,953.48 and 6, and we get 17,624, and we had, what was this other one? 17,857. So that's pretty close. Okay, so we're doing good there. 17,857, 17,857 equals, whoops, equals that divided by, probably did it wrong again, whoops, equals that divided by that. Okay, why is it, something's a little bit funky here, formatting, okay. That divided by that, okay, equals, the other one? Oh, was it divide not the right way? Okay. All right, guys. Sorry, and I think I flipped it again. So let me just do that. I had the division, the wrong sign. The backslash is going the wrong way. And that, and -1 to get the percent. Okay, so 0.13. So better than the other one. The other one is like 3% off. This is 1% off. We add in some decimal places. 1.32% off. And again, these are not going to be exactly right. It's an approximation, right? So pretty good with the trained testing. The model performed pretty well. And this says is a top seller based on this. Again, 82, 953, 48, and 6. And this is top seller, same one. And that's what I'm seeing here. So 82, 953, 48, 6. And we're putting in the, we're looking for the top seller. Is this top seller? Yes or no? And this is a top seller. Control Enter to refresh it. Top seller number 1. Okay, so we're doing good. 2/3 of the way done here, so stick with me to the end. Let's look at one more question. What employees will leave the company within 1 year? So again, we're going to do regression and classification on the same data set. The same thing that we did above. The regression task is to predict the number of months before the employee will leave the company or stay at the company, whatever way you want to look at it. It doesn't really matter. And then the classification part is predicting whether an employee will leave the company within the next year, okay? Within the next year, it's a binary outcome like we saw before. 1 equals yes and 0 equals no. So I don't have this information, right? I don't work in HR. I looked online, I didn't really find anything that really met the criteria of what I'm looking for, so I just created my own, okay? So we have age, tenure, salary, job satisfaction. So these are surveys, presumably, that is being done at work, which department you work in. And a lot of people can leave a certain department, right? Maybe the department head is kind of a horrible boss or something, and people just want to get away from him. That's possible too. So we're going to look at all these possible outcomes right here. Performance rating, that's definitely a determining factor in whether or not the person will stay. This performance looks kind of low. This one looks kind of high to me if it's measured on a scale of 1 to 5. And then months at company, that's what we're trying to predict, and will leave the company, yes or no. So let's look at the regression. I'll just refresh this, just so you know I'm not just making up stuff, right? I'll refresh it, and you can see in real time how this stuff works. So again, we have the, we're dropping months at company, and we'll leave. So there's 2 ways to do it. You can either take the x value, x variable, okay, and assign what you want to it, okay, or you can take everything and then just drop certain columns, right? So essentially the same thing. This might be a little bit less typing over here if you do it this way. So the x variable is the independent and the y variable is the dependent, just like before. We're doing our splitting, training, testing down here, and now we are using a random forest regressor. We saw in the example above that performs pretty well. It's better than linear regression in many cases, not always, but if you can get away with the linear regression, that's easier to set up, easier to execute, easier to explain to your stakeholders. If the performance isn't great, then go with something that's more robust, like a XGBoost regressor or a random forest regressor. Now we're using random forest. We're getting R squared of 1.0, so I'm pretty satisfied with that. And let's do the classification side of it. Okay, and the model is being fit and trained and test. Why train is not defined? Why is that not defined? Let me redo this. Something got jammed up here. Should be defined, right? Why should be defined? Why, it's saying why train. Let me see, did I not have the why train? Why classifier train? Oh, I see what's okay. So yeah, I did make a mistake. Why train? Oh, okay, okay. So y test, so let's see, test, that's for test. That's why, misspelling here. Y predicted, that's the y predicted. Okay, so we find there, and y test, yeah, and predicted. Okay, so that was it was a spelling mistake. Okay, should work now. Y train is not fine, but why is the y train? Y train, oh, y train, so that should be y regression train, y CLF train, I think that's what I called it. Y CLF train. Okay, that's it. Okay, so it should work now. Okay, nice. So we got a good accuracy 0.96 and the precision's 0.98. Um, this is a little bit low. I'd be a little bit concerned about that. But it's okay. This is not a video about balanced or imbalanced data sets and getting the best accuracy. I have videos on that. This is kind of a different focus here. So these numbers are low. I could probably pick a different model, random forest classifier, maybe the random forest or the XGBoost classifier might be better in this case. But you know what? I'll let it slide. I'll let this one go. It's good enough for our purposes what we're trying to do today. So let me look at this data set now. We're looking at 56, 10,600, 2.63, and 2.17. So is this the first row or the last? This is going to be the first row. Okay, so this is where the numbers are coming. 56, 10,006, 2.643, 2.17. We're trying to predict months at company. That's what we're trying to do. So the regression is coming first, months at company. Based on those variables, I'm going to say this individual is going to stay 71 months with the company, 74. So it's off a little bit. If we look at the difference here, 71, 74 equals divided by next one. So this is off about 4%. Not too bad. It's off a little bit, but that's okay. Again, we're making estimates here. It's not going to be exactly right, but it is pretty close to model was train tested, and we're using it to make predictions, and we're getting pretty close to what we want. So again, for the classification part, we've got everything set up. We are trying to predict, will the person leave, yes or no? This is a binary outcome, right? So we're not looking at numerics here as a numerical continuous variable. This is a discrete variable. It's on or off, 0, 1, true or false, yes or no. Will the person leave the company? We're saying 0 based on these numbers, 50, 6, 10,600, 2.6, 3, 2.1. And if we go back to this data frame, look at the first row, you'll see the same results here. And will the person leave? No, we're saying no. And that's what the model predicts. I'll refresh it just so you have full confidence that this is working in real time. And then just make this stuff up, right? So will the person leave? No, the person will not leave, given these features and these attributes right here, okay? So that is it, guys. So pretty quick, pretty painless. We've reached the end. Hopefully I've dropped some knowledge on you and you can take this and use it for your own benefit and solve your own specific problems based on the regression and classification types of issues that you're struggling with. Hopefully this answers your questions, and hopefully this was time well spent. I definitely learned a couple new tricks when I was putting together all the source code here and doing my research for this. Hopefully you guys learned a thing or two in the process as well. So that's it. I'm going to wrap it up here. Thanks for your time today. Enjoy the rest of your day. Goodbye.